Okay, so everyone can see my cursor, right?
Yes.
Okay, perfect. So today we'll be talking about the hardness of achieving fairness in cryptographic computations. So this is a joint work with my students Hamid Reza, Tamalika, and Mingwan. So as a representative example, we will be considering two-party coin tossing functionality. In this functionality, two parties interact with each other over R rounds. And at the end of the protocol, both parties agree on the output bit B, which is either 0 or 1. So this extremely simple yet elegant functionality helps us analyze the primary bottlenecks of achieving security in various adversarial models. Uh, in particular, this versatile results that we prove for this versatile functionality has consequences to various fields in mathematics and computer science. And very recently, there has been connections established to poisoning and evasion attacks on learning algorithms as well. So let me quickly introduce the notion of fairness that we will be studying in this talk. So we have two parties, Alice and Bob, and they interact for R messages, and at the end they agree on the final outcome bit B. During the execution of this protocol, the adversarial party may choose to abort, and at this point the honest party has to still output some bit. We call this bit his defense output. And an adversarial party can try to change the expected output of the protocol. And if it can change by at most epsilon, then we say that the protocol has epsilon unfairness. So I introduced this notion and I remarked that, that this is very different from the typical game theoretic notions of fairness. If there are any questions about this model, this is a good time to discuss that. Okay, then let's move ahead. So there are various ways we can summarize the state of the art before our contributions. I like to use Impagliazzo's words to summarize our results. I feel that this gives a very nice and elegant way of summarizing the state of the art. So in particular, we will be interested in three of Impagliazzo's 5 worlds. Minicrypt is a world in which one-way functions exist. So Pesiland is a world in which even one-way functions do not exist. And Cryptomania is a world in which more sophisticated cryptographic primitives like public key encryption and oblivious transfer exist. One way to abstract these worlds is to think of Pesiland as somewhere where cryptography is not possible, Minicrypt where fast cryptography is possible, and Cryptomania as some place where sophisticated yet slow cryptographic primitives are achievable. So let us try to understand the state of the art of coin tossing protocols in these worlds. So in general, if you do not have any restrictions on the power of the computational power of the adversaries, then using attacks on two-party zero-sum games, one of the parties can force a particular outcome with certainty. In 1980s, using one-way function, a new variety of coin tossing protocols were proposed in which the adversary can only change the outcome by 1 by square root r, where the round complexity of the protocol was r. Subsequently, Cleve in 1986 proved that irrespective of what computational assumption that you want to make, every coin tossing protocol is 1 by r unfair. So the intuition of this attack is that to begin with, there is entropy in the output. At the end of the protocol, there is zero entropy in the output. One of the party leads the other by 1 by r in entropy information about the final output. And that can be leveraged as an attack on the protocol. In 1993, an amazing attack was proposed. This restricted the class of the adversaries to fail-stop adversaries. These adversaries follow the cryptographic protocol honestly, but may refuse to participate or can abort during the execution of the protocol. So Cleve and Impagliazzo showed that a coin tossing protocol is 1 by square root r unfair, which is significantly larger than 1 by r. And amazingly, in 2009, Moran, Naur, and Segev came up with an amazing coin tossing protocol that relies on oblivious transfer. And this protocol is only 1 by r unfair. So it achieves the bound that Cleve proved. And such protocols are referred to as optimal coin tossing protocols because 1 by r unfairness is unavoidable.
So
So,
sorry,
yes.
does the result of Cleve 86, does he rely on anything more than fail stop?
No.
Okay.
So
So
he
this Cleve
gives
Impagliazzo is a strict improvement of Cleve 86.
Cleve 86, yes. The best way to interpret Cleve Impagliazzo is information theoretic commitment hybrid. If you work in that, they showed an attack of 1 by square root r. Any questions? Otherwise, okay. So let me color code these results. So what I have done here is the following. All constructions that are 1 by square root r unfair are colored green. And all attacks that are 1 by square root r unfair are also colored green. Red cells represent 1 by r unfairness constructions and attacks that achieve 1 by r unfairness. So given this, this colored representation, we can easily find open problems. Let's zoom into Minicrypt. Note that it is not clear whether the constructions of the 80s are optimal or the attack of Cleve is optimal. This is an open problem. This was an open problem before our contributions, before we made our contributions. Similarly, if you assume public key encryption exists, still we do not know whether there are better constructions or the attack of Cleve is optimal. In fact,
Sorry,
sorry.
I'm actually a little bit confused about this. So why doesn't the result of uh, Moran, Naur, and Sagev contradict the result of Cleve and Impagliazzo? Is it just because of the assumptions?
Yeah, because they are using oblivious transfer.
Okay.
So if
So this,
oblivious transfer exists, then Cleve Impagliazzo's attack does not work.
I see. Okay. So it's kind of a black box separation.
No. It's an information theoretic commitment hybrid result.
I see. Okay.
So oblivious transfer is significantly more powerful than commitment hybrid.
Hmm. Okay.
That's the main problem. And in particular, one can wonder why are there only two colors, right? Could there be blue constructions or are there blue attacks where blue corresponds to 1 by r to the power 3/4 unfairness, which is somewhere intermediate to the green and the red attacks. So all these problems were open before our contributions. So let me quickly summarize using this picture what our contributions are. So we were able to show that this entire region is green. This means in Minicrypt, where one-way functions exist, we show an attack that is that shows that any coin tossing protocol is 1 by square root r unfair. We also show in a subsequent work that if you are using public key encryption, still protocols are 1 by square root r unfair. We even extend this to more powerful hybrids where f is a function that does not enable oblivious transfer. Even in that hybrid, we can show that every coin tossing protocol is 1 by square root r unfair. Any questions at this point? So note, in particular, we have shown that in Minicrypt, these protocols from 1980s are qualitatively optimal. And let me highlight a subtlety of our result and how subtle our analysis has to be. Observe that if you have public key encryption plus seemingly innocuous properties like ability to sample a public key without knowing its corresponding private key, then it already implies oblivious transfer. So our hardness of computation results have to avoid such subtleties. In fact, our public key encryptions, like the vanilla public key encryption, which does not have these properties, we crucially rely on such absence of innocuous properties that people typically tend to assume. Any questions at this point? So this picture might give a false impression that we resolved everything. There is no gap left. But let me tell you an open problem, which I feel is one of the biggest open problems in this field. Suppose f is a function that does not enable oblivious transfer. Assume that there exists a secure protocol to compute f. This assumption is stronger than just providing access to f hybrid. Let me elaborate on this slightly. A protocol for f can be used not just to compute f securely, it could have other applications as well. And our result does not rule out these inconceivable ways of using the function f, the protocol for f. Okay, so this is one of the biggest open problems remaining in this field, and it is one of the most challenging problems in this area. Okay, so let me quickly introduce the main. Let me quickly summarize the main technical idea that led to all these results and breakthroughs. So there are two different interpretations to the technical contributions that we make. If you approach it from a combinatorial perspective, then it yields most secure coin tossing protocol designs. So in particular, we can answer questions of the following form. What is quantitatively, not qualitatively, quantitatively the most secure coin tossing protocol if you are willing to assume the existence of one-way functions? Interestingly, it's not the majority function extractor. We'll discuss about this later in the talk. There are protocols which are better than these protocols quantitatively. And these have also connections to isoparametric problems in product spaces. If there is time at the end of the talk, I will discuss these connections as well. If you take a more algebraic perspective, then it yields new analysis techniques in complex models that yield black box separation and hardness of computation results. In this talk, we will be taking this algebraic perspective into our into the new technique that we have proposed in these works. So one thing that you might observe, that typically construction of secure protocols and constructing attacks on secure protocols employ entirely different technical tools. Our new technique unifies these two fields. So our attacks are inherently constructive in the sense that they yield as a byproduct the optimal secure protocol as well. So let me summarize the key technical result that we will prove in today's talk. So if there is a coin tossing protocol of R rounds that uses one-way functions in a black box manner, then we shall prove that this protocol is at least 1 by square root r unfair. And this kind of a result is referred to as a black box separation result. It was introduced by Impagliazzo and Rudek in 1989. And separating coin tossing protocols from one-way functions imply that they are more complicated cryptographic primitives than one-way functions.
But wait, so isn't the same theorem known, but for commitment schemes?
For commitments, we can construct commitment from one-way functions, right?
Yeah.
And that also black box manner, right?
Yeah, that's true. So your theorem in some sense subsumes the...
Yeah, we are saying that, yeah, we'll come to that. We'll subsume all previous results.
Okay.
Yes. So interestingly, this analysis will also exist to public key encryption. We'll show us, we can show a separation from public key encryption as well. And even when we have F hybrids, like you can compute complex functions, like very complicated functions, but these complicated functions do not suffice to give oblivious transfer. Then we can also show this separation. Any questions? Then we can move to more the literature survey part. So let me quickly summarize the state of the art before our results. Suppose we are in minicrypt, so one-way function exists. Therefore, there are commitment schemes. Then in 1980s, the following protocol was proposed. Alice commits to independent random bits x1, x2, xr. Bob commits to independent random bits y1, y2, yr. And every round, Alice and Bob reveal one bit at a time. Then you define zi as the XOR of xi and yi. And finally, the common bit that both parties agree on is the majority of these bits z1, z2, zr. So interpret majority as an extractor that is applied on these bits. And what one can show is that a party can abort during the execution of this protocol and change the output distribution of the honest party by 1 by square root r. Basically, the attack waits till the last round. If the number of ones and zeros are balanced, then it aborts in case of heads and continues the protocol in case of tails. This attack gives a 1 by square root r attack. In 2009, an amazingly elegant protocol was proposed, which does the following. Suppose oblivious transfer exists, then parties use oblivious transfer to choose a magical round I star. This, given this magical round I star, they pick random independent bits z1, z2, zr with the following property. The random bit loses its entropy starting round I star. There is no entropy left. Then Alice and Bob receive additive secret shares of the bits zi's. And the final bit is XR XOR with YR. So an attack on this protocol effectively reduces to guessing the magical round I star. So that is possible only with probability 1 by R, and hence this protocol is 1 by R unfair. These are the two protocols that are known. The first one was using one-way functions and the second one using oblivious transfer. So now let's move to hardness of computation results. So if an attacker is malicious and has unbounded computational power, then it can attack using attacks on two-party zero-sum games or games against nature. And these attacks can also be performed using a rejection sampling technique if one-way functions do not exist. And this result was proven only very recently in 2014. However, if we restrict the class of the attacker to fail-stop attackers, that is where the adversary will follow the protocol honestly and may choose to abort sometimes during the execution of the protocol. Then Cleve Impagliazzo's result says that any coin tossing protocol is 1 by square root R unfair. Recently, just a couple of years ago, Iftaq and others proved the following amazing result. They showed that if R is a constant, then there is a universal constant C such that this, if a coin tossing protocol is less than C by square root R unfair, then it implies key agreement protocols. So I want to highlight that key agreement is a more complex primitive than one-way function. So key agreements, existence of key agreement protocol implies one-way functions. So this shows a stronger consequence. However, this is for an extremely restricted class of protocols. Here R is a constant. I state this result up front because this is the only result that we will not subsume. Any questions? Okay. In 2013, Iftaq, Omri, and Zarosim proved that we can simulate Cleve Impagliazzo's attacks in the random oracle model, or in a model where parties have access to one-way function if the function has no inputs. So this gives hope that maybe we can implement Cleve Impagliazzo's attack on coin tossing protocols. However, observe that this result holds only for semi-honest adversaries, that is honest but curious attackers. And there is no honest but curious attackers on coin tossing protocols. So this hope was very short-lived. In 2011 and 2014, there were two results which prove that if coin tossing protocols use one-way functions as a black box in a black box manner, then achieving 1 by square root R unfairness is difficult. However, the restriction that they had was that their round complexity was only sublinear. Okay, this was a significant restriction, sublinear in the number of, in the input size of the one-way function. So here is the result that we prove, and this is the result I will actually prove in this talk. Suppose there is a coin tossing protocol pi that has R messages. The expected output is X. Then there is an attack which can change the honest party's output by variance of X divided by square root of R. And I want to emphasize that this is just a pure mathematical result. There is no asymptotics involved. So let me elaborate on that point further. X and R can depend on N, the input size of the one-way function. X could be 1 by polynomial in N. All these are dealt with in this by this theorem. We do not need any, this is a general theorem that holds for whatever value of X you wish to plug in. This in fact proves the qualitative optimality of the coin tossing protocols that were proposed roughly 3 decades ago. However, I want to emphasize that this is only a qualitative optimality. We know of protocols that are, let's say, 60 to 80% better than the protocols that were proposed in the 80s. However, we do not have a theoretical analysis of these attacks. We have experiments to show that these attacks, these coin tossing protocols are significantly more secure than the protocols proposed in the 80s. Any questions at this point? Okay. So let's set up a formal setting where we'll prove our results. So we will be working in the information theoretic random oracle model. So let me first define what a random oracle is. A random oracle is a function from n-bit strings to n-bit strings that is, and such a mapping is chosen completely at random. What it means is that old queries to the function will be answered consistently, However, any new query is answered independently and uniformly at random. I want to emphasize that parties, Alice, Bob, and the adversary, all of them have unbounded computational power. We are working in the information theoretic random oracle model. Note that if Alice and Bob queries are disjoint, then a random oracle is just answering queries randomly, and this can be easily simulated. However, complexities arise if Alice and Bob have common private random oracle queries. And this is the entire complexity of the analysis to handle such queries. And more complexity is arising out of them. So a coin tossing protocol in the random oracle model has the following structure. We have two parties, Alice and Bob, who are interacting over a R-round protocol, and each of them can ask n private queries to the random oracle. At the end of the protocol, both parties agree on the output B. And if at any point in time, let's say Bob aborts, then Alice outputs a bit known as her defense bit, represented by DA. If Alice aborts, then Bob outputs his defense bit DB. And these defense bits are updated only when parties are preparing next messages of the protocol. And X will again represent the expected output of this protocol. So the intuition that I want you to have is the following. Random oracles are idealized versions of one-way functions because these are very difficult to invert even with unbounded computational power and exponential number of queries. So random oracle will serve as a proxy to one-way functions. Another way to interpret it is that one-way function will be an idealized or most difficult, hard to break function. So here is the problem setting. We will be given a protocol pi that has R rounds with expected output X, and parties have query complexity N in the information theoretic random oracle model. Our objective is to construct a fail stop attack that changes the honest party's output distribution by variance of X divided by square root of R. So before we delve deeper, let me introduce some technical results that will be needed to prove our results. The first concern that one encounters is the following. In the random oracle model, the views of the parties Alice and Bob are correlated via the random oracle. How can we remove this? So there are by now standard techniques to remove the correlation between Alice and Bob. So these algorithms are called heavy queryers. And what you do is that you perform more additional queries to the random oracle. And given the answers to these additional queries, the correlation between Alice and Bob private views is broken. Let me emphasize the subtlety here. What I'm saying is the following. Before a heavy query starts, we can assume that Alice and Bob views are independent, conditioned on the public transcript. After the heavy query terminates, at that point, again, we can assume that Alice and Bob views are independent, conditioned on the newly evolved transcript. However, the evolution of the transcript itself is correlated with the private views of Alice and Bob. This subtlety is the crux of the complexity of analyzing protocols in the random oracle model. So we henceforth will assume that we have a protocol that already employs the heavy query, and we can assume that Alice Bob views are independent, conditioned on the public transcript. And that is all that we are going to assume. No additional assumptions will be made. So our analysis proceeds at a high level by induction on round complexity. This is a very significant divergence from existing approaches. Our inductive step will use a potential argument, and this potential argument will use a global invariant which is specific to augmented protocols in random oracle model. Without this global invariant, our attack will not work. So the analysis is extremely subtle. So let me first introduce the potential function that we'll be considering. So it will be a function of three variables, x, a, and b. The first term of this potential function is variance of x. The second term is intuitively represents the distance between x and a. And the third term represents the distance between x and b. So let me give you some intuition behind this potential function. X will be, so let's fix a partial transcript tau of the protocol. Conditioned on this partial transcript, we can compute the expected output such that the full transcript is consistent with this partial transcript. This will be the value x. Suppose at this partial transcript tau, Bob aborts, then Alice has her defense coin. The expected value of Alice's defense will be A. Similarly, the expected value of Bob's defense will be B. So the three terms here have the following intuition. The first term measures the quality of the attack owing to the entropy in the final output. If the final output is already decided that it is close to 0 or close to 1, then we will not be able to attack it significantly. The second term measures if Alice is performing a bad defense, then she should be punished for it. Let me give an example. Suppose the expected outcome is half, but Alice is choosing to defend using a defense such that her expected outcome is 1/4. Then Alice can, at this point, Bob can just abort, and Alice's output distribution will have expected value 1/4 instead of the honest output of half, which are significantly distributed. They are significantly different. So in some sense, this term punishes Alice for defending badly. Similarly, this term punishes Bob for defending badly. However, let me add the following disclaimer. This intuition is only in hindsight, okay? There may be more functions that you can construct that mimic these or capture these three properties. We have not been able to prove our result using those potential functions. So this is only an intuition in hindsight. So a key technical contribution that we have to, that we make is Jensen's inequality for this potential function. So let me elaborate. What does this mean? Suppose we have a partial transcript tau and the protocol evolves to a new transcript tau prime. So the expected output at tau prime, if you take an expectation of all possible evolutions, then it is the expected outcome at condition on the partial transcript being tau. Similarly, expectation of Alice defense in the future is Alice defense now. Expectation of Bob's defense in the future is Bob's defense now. So we have this potential function. We have a partial transcript tau, and there are various possibilities that this transcript can evolve into. Suppose the protocol evolves into partial transcript tau prime. At this protocol tau prime, we have a potential x of tau prime, a of tau prime, b of tau prime. And we are computing the expected value of this potential function. At the root, we have the potential of the expected values. So now we need to compare the potential of the expected values with expectation of the potential values. We would like to prove that the quantity on top is greater than equal to the quantity below. However, this function is not convex. In fact, there are values that one can assign to these random variables such that Jensen's inequality is false. It does not hold. We prove that Jensen's inequality holds if these x tau prime, a tau prime, b tau prime are generated from x tau, a tau, b tau using an augmented communication protocol. So our results, this is a very precise result in the sense that it can distinguish augmented communication protocols from general probability distributions. So let's quickly see how we prove this result. So we want to compute the expectation of the future potential. So we write down the potential expression as the sum of 3 terms. This is the most key step in this entire proof. This expression can be rewritten as this new expression. Now we apply linearity of expectation to this term, and we get 3 different expectations. Note that the first is just x tau. The second term here, we can move the expectation inside by using Jensen's on the function z square. By the way, this is the first place, and in fact will be the only place where we have an inequality in our derivation. Next, we have to compute the expectation of the product of the differences. So this part uses the augmented property of the coin tossing protocol and says that the expected value of the product is the product of the expectations. And then we get the final expression here, which can be rearranged to the potential at the root. So we have proven a Jensen's inequality for our potential function. And this is true only for augmented coin tossing protocols and not for arbitrary probability distributions. Any questions at this point regarding the proof? So I just want to highlight that this is the only inequality in this entire analysis. If you are wondering whether this is tight or not, it's if and only if this inequality is tight. We'll need one more technical lemma. Let me give the intuition of what this technical lemma means. I will not prove this. So suppose we have a partial transcript tau, and there were R messages subsequent to this partial transcript that were remaining. Take one step of evolution of this interactive protocol. The updated transcript is tau prime. At this point, only R-1 messages remain. As an adversary, I can decide to abort at at the partial transcript tau prime. At this point, the quality of my attack is measured by this potential function. If I choose to defer my attack to a future point in time, to this subtree, then it will be measured by this quantity. I want to emphasize that the denominator here is square root of R-1, representing that R-1 protocols remain, R-1 messages remain in this protocol subsequent to realizing the partial transcript tau prime. At this point, an adversary can choose one of these two attacks depending on whichever is larger. So this technical lemma says that this quantity is greater than or equal to the potential at that partial transcript tau prime and some factor outside. I want to again highlight that R-1 changed to R here. So basically, the denominator, square of the denominator keeps increasing by 1 as we go one step up the protocol. Okay, now we have the two technical results that are sufficient to prove our main result. And our result will prove the following: that the optimal attack on a coin tossing protocol is the potential is given by, sorry, is the measurement of the optimal attack on a coin tossing protocol is lower bounded by variance of x, that the expected output, divided by square root of r, where r is the round complexity. And by an averaging argument, one can show that this gives an explicit attack because there are 4 types of attacks that are possible. Alice or Bob can increase or decrease the expected output. So one of them must be at least 1/4 this quantity. So this main technical result suffices to prove our hardness of computation result. We'll prove this result by induction on R. And let me show this proof. It's a very short proof. Suppose tau is the empty transcript. That is, the protocol has not begun yet. Tau prime is the first message that the first party sends. Pi tau prime represents the protocol conditioned on the first message being tau prime. By inductive hypothesis, we know that the optimal attack is greater than equal to the variance of the expected output at tau prime divided by square root of r minus 1. We had argued earlier that the optimal attack works as follows. The adversary at every tau prime can choose one of the 2 attacks independently. Let me elaborate on this further. For every message tau prime, the adversary can choose either to attack at that point tau prime or defer the attack to the subsequent r minus 1 round protocol. By inductive hypothesis, we know that this term is greater than equal to this expression here. By technical inequality, we know that the maximum of these 2 is related to the potential of the 3 variables x, a, and b at tau prime. By Jensen's, we can push the expectation inside and we get the x, a, and b at tau. Now we can expand the potential function. Note that these 2 quantities are non-negative. So this is at least the variance of x. X tau is x in this expression. Any questions about this analysis? Okay, so let me quickly summarize the theorem that we have proven. Suppose we have a R message protocol, coin tossing protocol pi, that makes n queries to the random oracle. Parties have unbounded computational power. X is the expected output of this coin tossing protocol. Then we construct an attack that can change the honest party's output by variance of x divided by square root of r. And this attack performs polynomially more additional queries to the random oracle. This result translates into a black box separation result that basically states that if a coin tossing protocol uses one-way functions in a fully black box manner, then we can swap out the particular instance of the one-way function with the idealized one-way function, namely the random oracle. And we attack as we have we attack using the adversary produced by this technical result. Any questions at this point? So we can extend this result to more sophisticated models where parties can use a, a public key encryption oracle as well. And this also result extends to hybrids where parties are given ideal access to computing functions that do not yield oblivious transfer. And there are several ongoing works that we have currently. One of my favorite results here is that we were able to show the existence of qualitatively better protocols than the ones that were proposed in the 1980s. And these protocols are a, the optimal protocols that we construct are roughly 60 to 80%, sorry, they are 20 to 40% less insecure than the protocols that were known in Minicrypt. One of the most fascinating connections that we establish are the connections to new isoparametric inequalities. And let me discuss this because this has me really excited. So let's take a product space where sigma represents an alphabet set. So intuitively, you can think of sigma either as a small alphabet, for example, binary 0, 1, or you can think of a very large alphabet, for example, natural numbers. Suppose we are given a set S that is dense in the product space. Then we have the complement of the set defined as S complement, represented here by purple. The vertex perimeter of the set S is the set of points lying in S complement that are neighbors of points in S. So let me define neighbor. 2 points are neighbors if you can change one coordinate to move from one point to the other. So del S represents the perimeter, I will call it the outer perimeter of the set S. If sigma is small, for example, the binary alphabet, we know that a dense set has a dense perimeter. For example, if S has density half, then the perimeter del S is 1 by square root n dense. However, if sigma is very large, for example, natural numbers, the set of all natural numbers, then we know that there are dense sets with very small perimeter. The density is only 1 by n, not 1 by square root n. Okay? If you take a cryptographic perspective into this problem, then one should not just consider the outer perimeter del S, we should also consider the inner perimeter del of S complement. And the cryptographic objective is to minimize the maximum of these two perimeters. So what we prove is that the maximum of these two perimeters, the inner and the outer perimeter, is well behaved even for large alphabets. We can prove that this maximum is the maximum of these two perimeters has density 1 by square root n, irrespective of the size of the alphabet. Interestingly, the optimal sets that achieve these perimeters are not the sets that you would typically come up with. They are called, you can imagine Hamming balls. They realize the optimal constructions for when sigma is small alphabets like binary. For large alphabet, that's not the optimal construction. We are able to prove that the Hamming ball is actually 2 or 4 approximate of the optimal construction. Any questions at this point? This is the final slide. I will just conclude after that. If there is any questions about this new problem in isoperimetry that we have been looking at, it will be really interesting.
So do you have a sense of what the optimal sets are for?
So this is a very interesting question, actually. We give a efficient algorithm to construct that. It is a recursive construction. We do not have a succinct uh, summary of those sets using elementary functions. But we have a efficient algorithm that recursively calculates it up to arbitrary precision. So this actually also motivates that you can study not just the L infinity norm of these two perimeters. You can consider smoothened version of it like L1, L2, other various L norms. And we, in fact, study the L1 norm of this, which is well behaved. And it is a two approximation of this cryptographic problem. Okay, so with that, I would like to conclude my talk. I would really like to thank my collaborators, my students, Hamidreza, Tamalika, and Mingwan. And without them, all these works would not have been complete so quickly. And I really want to thank thank the support that I received from various funding agencies during my time here at Purdue. And yeah, many of these research have intersected with the research that I presented in this talk. Thank you.